happy birthday to Chris Kirk. Is that true? Yeah. In honor of your birthday celebration, we have a special program hand-selected for you. We know of your deep and sincere interest in archaeological sites in Shrewsbury and your dedicated work in documenting those through the Historic Commission. So Tom has graciously accepted to come and present about old mills and water power. Tom's PowerPoint presentation tonight shows how water power worked and the role that mills played in early America. Several types of dams, water wheels, and mills will be explained. Tom is historian and curator of mechanical arts at Old Sturbridge Village. He's done many presentations throughout the country, including many here. He's one of our favorite presenters. Tom holds a master's in history from UConn and writes for several magazines, including Early American Life, and he has a feature article in this current issue of Early American Life. So we welcome Tom back to the podium.
Thanks very much. Thanks for having me. Yeah, and the other thing is I've been running water-powered mills for over 36 years now. Haven't helped me. So hopefully some of my stuff isn't too basic, but I do want to get the idea. Of course, water's everywhere. It's necessary for life, and our planet is more water than land. But that water doesn't usually do much for mills except tide mills. But water has weight to it, like everything else. And it weighs a little over 8 pounds a gallon. And water power is really nothing more than gravity. So when water falls, energy is released. Most of the time, the energy is just dissipated. It's not used for anything as water runs to the sea. It's very pretty, and of course attracts tourists to a lot of places around the country and around the world. It can be very soothing, can be very destructive. Here in New England, we tend to have a lot of it, as it's raining tonight. But we also tend to have a very rolling landscape. We have a lot of hills, and that allows a lot of the rivers to have a good amount of fall to them. There's places in the world, places in this country, where you don't have the fall that we have here in most of New England to be able to have thousands, literally, of mill sites in just this small part of the country because of the topography of the area. But like I said, most of the time, it's water power is an untapped resource. It's just providing ecosystems and scenery and nice soothing noises and the like, but not generating energy for our use. For a lot of the history of humankind, the biggest source of power to get anything done was muscle power. Usually people, sometimes animals, and in a lot of the world that still goes on. And of course, one of the first things that people put water power to was substituting what all these people are doing, which is grinding grain, taking the hard seeds of what are called farinaceous grasses, starchy grasses, like wheat, rye, corn, oats, barley, rice, etc., and breaking open the hard outer shell of those grains and making it much more digestible for us. In ancient times, thousands of years ago, they started to come up with better ways than just pounding grain to reduce it and using stone to do that. Still using muscle power, either people or animals, to grind the grain, but nonetheless using stone to grind it. And here's a happy little ancient Roman or Greek, it doesn't really matter, standing next to an early mill where you can see it's kind of almost like a little hourglass kind of thing with the meta and the catillus to hold the grain in the funnel kind of portion of the top, and then as it passes between the two stones gets reduced, gets ground up. We'll get into more of that. Like I said, the idea at first from those saddle stones that some of the people were using, like the Egyptians, were just rubbing one stone over another, to the continual motion of rotary motion, and that you can then have people or animals do for you, makes it a lot more efficient to grind grain. Of course, there's other things that people applied water power to later on. One, of course, was reducing logs into lumber, and, of course, working textiles. And we'll get into that a little more later on. Not just spinning, but carding and weaving, all the different steps in making textiles. But back to water and water power. The water wheels go back thousands of years. The gentleman at the bottom here, Marcus Vitruvius Pollio, pretty much described a water-powered grist mill in the 1st century BC. He wrote a book called 10 Treatises on Architecture, and in it he basically doesn't say, I got this great idea, but he says, if you've never seen a mill run by water, as opposed to donkeys or slaves, let me tell you how it works. And he pretty much describes the mill that we've got at Old Sturbridge Village, that they've got at Wayside Inn, that I've been showing you pictures of, and I'll show you more. Taking the advantage of falling water with a big wheel, and then turning one stone above another to grind grain. So it's nothing that's new. It's a very archaic technology. It's much, much older than buttons, which don't even come until about 600 years ago. Actually, buttons come about 700 years ago. Buttonholes come about 600 years ago. But water-powered mills go back a couple thousand years. Anyhow, the Romans sometimes had these series of mills built into a hillside. This one in what's now France, using the same water over and over again as it falls progressively, rather than build some very, very large wheels that had a lot of smaller wheels that could take advantage of the continual fall of the water to harness energy. But anyway, here in America and across Europe, these mills were ubiquitous. In the 11th century, of course, 1066, William the Conqueror conquers England. 1088, he decides he needs to figure out what he's got so he can tax it, and he has a massive survey done. It's called the Domesday Book, and that records well over 5,600 water-powered grain mills in England. You count that against the English population at the time, you've got like a mill for every 50 people. It's an amazing amount of water power. These are often very, very tiny mills, of course, probably, but nonetheless, using water power to do work that had been done by people, and that's 1,000 years ago. In the United States, by 1840, you've got over 23,000 grist mills, over 31,000 water-powered sawmills in 1840 here in the United States. So these mills were everywhere. Most towns had at least a handful, some had dozens. But to harness the potential energy of the water, usually you have to dam it. There's very, very, very few naturally occurring mill sites. There's sites where water has fall to it, but to get an efficient way to harness that water, you need to do an awful lot of modification of the landscape. To my mind, an amazing amount of digging and damming, moving hundreds of tons of earth and stone and sometimes wood to control the river, to get that gravity to let the water fall all at once so you can more efficiently harness it. And so very often, you know, when people take walks in the woods around here, they'll say, oh, this would have been a great mill site. They didn't have to do much. Oftentimes, if you look close, you'll see that what it was, the land has been modified, but it's going back into nature, because not all dams were made of stone. Like this one here, a lot of them were made of just earth and wood, and that doesn't tend to last forever, but it still changes the landscape considerably, because the river doesn't completely wash away the earth once the wood rots. Anyhow, so one thing to keep in mind about old dams is a lot of them did incorporate a lot of all wood or largely wooden components. I really like this one on the top here, where they have underpinnings, basically timber frame, to support boards to back up the water. So the mill pond, the water was up here, and this just held it back, using some stones, but an awful lot of wood. And you see that in a lot of dams, sometimes just logs, but because of course wood is a lot easier to work with than stone, and has a lot of advantages, because you got to remember, people don't live forever, and most people who owned mills tended to only own them for a decade or two, whether they died or they just got out of the business and sold it. You don't have to necessarily invest the time and money to make things last forever. To give you a very crude personal example, a year or two ago, I work at Old Sturbridge Village. I was putting a new roof on a privy next to our schoolhouse, and I was up on a ladder laying a wood shingle roof, and somebody asked me how long the roof would last, and I told them it was going to last forever. And they looked at me curiously, and they said, "No, really?" I said, "No, this is a forever roof. It's going to last forever." And they said, "No, really, how long is it going to last?" I said, "Look, I'm 60 years old. I'm not going to be on this ladder 30 years from now replacing the roof. As far as I'm concerned, this roof is forever." So, but I think that gets the point across that we sometimes forget when we look at back at history. We tend to think in the long historical term, and forget that we all have just a very short span of the long historical term. Anyhow, it's another one of these combination earth and wood dams. And there were a whole bunch of illustrations in books in the 19th century describing how to build various dams like this, some of which were very economical in their use of wood. Just a lot of boards and a frame underneath in what's called the air face of the dam. You have the water face and the air face of a dam. But also putting cribs of logs together, filling it with dirt, filling it with rocks. And sometimes if you've got a lot of logs, laying them down. The advantage of doing this here is that when water gets high and goes over the dam, so it doesn't wash away the soft banks and collapse everything, you need to have something to protect a soft riverbed. You could lay stones down. This is called riprap, to break up the force of the falling water. You can see it here. If you're building on ledge, you don't have to worry about that, because it's going to take tens, hundreds of thousands of years for the water to wear away the ledge stone, and you don't care at that point. But for the short term, either riprap of loose stone or this apron of logs to absorb the force of the falling water and protect the soft bottom of the stream is important. Throughout New England, this is in Killingly, Connecticut, you can, if you go through the woods, and sometimes just by the sides of roads, you can see sometimes amazing surviving stonework from some of these now long gone mills, and the considerable amount of engineering and just plain hard work that went into putting these things together. Sometimes with subterranean cavities for all sorts of things, using water rams to use water power to pump water for other purposes, sometimes using putting your water supply underground so you don't have trouble with debris clogging things up. You don't have trouble with it freezing up in the winter time if you put it underground. But very often when you're building with stone, you're taking advantage of not just muscle power, but some mechanical advantages, using cranes, gin poles, to move the stone around and get it in position. Anyhow, and sometimes you got stone work dams that are, I think, works of engineering beauty. But you can see out here they've done a staircase to break up the force of the falling water. And sometimes it's not as elegant. But anyway, so a few basic terms. There's a lot of, like anything, there's a lot of terminology, and I won't subject you to all of it. But a few basic terms is you get water to and from a mill in a race. The head race supplies the mill, and the tail race is the exhaust pipe, like a tailpipe in a car. It takes it away after the water's been used. This is actually at the Gilbert Stuart birthplace in Rhode Island. They have actually got 2 mills on site. So these are some head races. This one here, elevated. Sometimes the topography is such that you really cannot get the water to the mill through the ground. You need to elevate it up in a sluice or a flume. Originally just open wooden ones like this one here. Later on, of course, they'll come up with iron and steel pipes to supply the water to the mill, like in the lower left here. But you always need a way to control the water as well. And so you have what are called sluice gates, basically just sliding doors. Usually they're very simple, that just go up and down and allow the miller to control the mill. It's the on and off switch of the mill. The thing on the lower left is called a Flyball Governor. It uses centrifugal force and gears to control the height of the gate, how much water is going in your mill, depending on how fast the mill is going. That's not something your neighborhood grist mill or sawmill or fulling mill would have, but in textile factories where you've got dozens, hundreds oftentimes of machines all running and going on and offline, you can't really subject them to dramatic speed fluctuations, especially if you're processing textiles, all the threads will break. So they often have these Flyball Governors from the late 1700s on to automatically control the water going into your mill and keep everything running at a fairly steady speed. Sometimes you get more complicated gates with threaded iron rods and screws and ratchets and rack and pinions and all sorts of fancy ways to move the gate up and down, but sometimes it's just a matter of lifting it with a lever. I put this one in because this is a gold stamping mill in a book called De Res Metallica by Johannes Agricola in the 16th century. I love their little medieval get-ups. Actually, I saw a mill very much like this in Romania about 20 years ago, which I was surprised to see. Such primitive technologies continuing to survive into the well, then 20th century, but the very end of the 20th century. So anyway, the basic idea of water power, I said, is gravity. So a few more basic terms is flow, the amount of water you have, and the head, the distance the water falls. But the power equation is very simple. Head times flow equals the power. So if you have a flow of 10 gallons a second dropping 1 foot of head, you get the same amount of power as if you had 1 gallon of water per second dropping 10 feet. That's as far as the math is going to get here. I'm not an engineer. But anyway, some basic early types of water wheels are here illustrated: the overshot, the undershot, the breast shot or a breast wheel, and a pitchback water wheel. The earliest ones in use, the ones that they were using in ancient Rome and ancient Egypt, were these undershot wheels. Just basically imagine the back end of a Mississippi riverboat, but without a steam engine, just letting flowing water hit the paddles at a very tiny portion of the circumference of the wheel and providing an impetus to turn the wheel. That's a very relatively simple wheel to build and simple wheel to use. You often do have dams and flumes, but you don't necessarily have to. It works better when you can control the water, but very little of the wheel is actually weighting, it's actually in contact with water. So for the size of the wheel, you don't really get a whole lot of efficiency out of it. Most of the water is not doing work, but just the power is running to waste. The simplest way to employ an undershot wheel is what are called river mills. Basically, you put your mill on a boat and put it in a fast-moving river. In medieval France, the Seine had dozens and dozens of these river mills tied up to bridges and to the shore. And as the river flowed through Paris, they had all these little mills. So this one is in Eastern Europe. Here's a few more in Eastern Europe. The lower right is Romania, and I think the upper left is, I'm not sure where it is. Anyway. But anyhow, so the undershot wheel is the simplest. In the Middle Ages, they came up with the Overshot Wheel. The idea being that you put water over the top of the wheel and have the water enclosed in little troughs, little buckets. It is not so much just the impact of the water hitting the wheel like in an undershot wheel, but here's the dead weight of the water is making this whole side of the wheel heavier than this side. So the water held captive as it falls is forcing the wheel around. And because you're using water on half the circumference of the wheel, you're getting a lot more efficiency out of the water. And you got a lot more head, a lot more fall. There's a lot of disadvantages to the Overshot Wheel because it's prone to what's called backwater because of the direction it flows. I think I got a better illustration. Yeah, I do. Because of the direction the water flows, the bottom of the wheel will churn up. So if the level of the water, the tail race goes up, the water wheel is trying to push everything back upstream and it comes to a dead stop. So it's not at all a good choice if you've got a site prone to flooding. It's not a good choice unless you can get the water to drop 12, 14, 16 feet, probably at least 14 feet. Most of the early millwright books say that it's not even worthwhile to build a mill with an overshot wheel that's less than 12 feet in diameter, because a lot of what it is torque. I wasn't going to use another technical term, forgive me, but torque is twisting power, if you don't know. It's just twisting power. It's leverage. So think of this as a lever. So if you've got a 16-foot wheel, this is an 8-foot lever, and with all this weight on the outside pushing an 8-foot lever, exerting a lot of force to give you your energy. Very often, because it is efficient, because half the water wheel's circumference is suffused with water, they don't always have to be very wide. They can often be very narrow, and sometimes they have to be if your flow, the volume of water, is fairly limited. In the late 19th century, they started not only building a lot of wood, but out of steel. This is what's the upper left is what's called a Fitz wheel. The Fitz water wheel company made turbines, but they also made these overshot water wheels. And of course, they could make them in factories in parts and then ship them out to site and be assembled. And the iron and the steel was much more smooth. You had a much more hydrodynamic curve to the buckets, so it was much more efficient. And they were less prone to icing up than wooden wheels. They tended to last longer than wooden wheels. This is probably the most photographed mill and painted mill in America. This is the Mabry Mill. It was built in 1910 in Meadows of Dan, Virginia, on what's now the Blue Ridge Parkway. It's a beautiful part of the country if you ever go down there. I, over my desk at work, have a postcard that I bought at a drugstore years ago that has a picture of the Mayberry Mill. And in a big ribbon across it, it says, "Greetings from Massachusetts." Southwest Virginia. Anyway, this in Georgia is the largest water wheel ever made. I believe this is something like 60 feet or something like that. It's a big water wheel. Obviously, it's iron, it's not wood. You can't build a wheel that big. But again, look at what they've gone to get the water over the top. So anyway, there's a lot of disadvantages to overshot wheels because they're fussy. They're efficient, but they're fussy. A sort of compromise, if you do have a lot of head, a lot of drop to the water, is the pitchback wheel. The water is delivered just behind the downstream side, the tail race side, and instead of the wheel churning this way, the wheel with the weight churns this way. So you're using almost half the circumference of the wheel, but if this floods, too much of it will cause friction on the wheel, but it's not churning, it's pushing the water away from it. It's not trying to churn it back up like an overshot would. So it's got that advantage. The most common water wheel in 19th century America, 18th and first half and beyond of the 19th century in America, and longer in a lot of the rest of the world, was the breast water wheel, the breast wheel. The breast wheel is sort of the compromise It's got the best of all possible worlds as far as water wheels go. The breast wheel has the advantage that you can deliver the water at a lot of different spots along the wheel. So you're not as tied to always having to have a high head. You can have backwater flooding in the tail race because it's like the pitchback pushing the water away from it, not trying to churn it back upstream again if it's waiting, if it's in standing water. You can make them out of iron. You can make them out of wood. So they're relatively efficient. So it's a good compromise. In 1840, there were over 1,000 factories here in New England, and just about every one of them was run by a breast wheel. And a lot of the little grist mills and other mills around New England, fulling mills and such, were also often run by breast wheels because they're a good compromise of practicality and efficiency, and can operate on a lot of different sites. And if you've got the illustration, you can see how the water, like an overshot wheel, fills the buckets, makes one side of the wheel heavy, and as it falls, it pulls the wheel around using that great leverage of the large diameter. But at the bottom, it lets the water go on its merry way downstream. It's pushing the water away from itself. So the breast wheel's a really workhorse of industry. And if you've been to Old Sturbridge Village, our grist mill has a 16-foot high, 8-foot wide breast shot wheel, and it works quite well. Another arrangement of water wheel that had been used for well over 1,000 years, probably 2,000, is what's sometimes, usually historians call it a Norse wheel because they notice people in Viking areas using it. The Greeks used it, the Iberians used it, the Romans used it. It's not just the Vikings, but some people have to get the credit, and they gave it to them. So anyway, but all it is a vertical axle. Think of it kind of as an undershot wheel turned sideways, because the water comes in, hits these paddles, and it's not dead weight like the overshot or the pitchback wheel or the breast wheel. It's the impact of the water flowing that's pushing things around. It's a really, really easy wheel to build. It's easy to maintain. If you're running a grist mill, it's great because you don't need to go through extensive gearing like in Vitruvius's mill. Here, all you need to do is put a millstone on the top of an axle, paddles on the bottom, and away you go. They can make them out of sheet iron, which they start doing in the early 19th century. They can make them out of carved wood. In Europe, you see a lot of these carved wooden wheels, little scoop scallops to make it more efficient than just straight paddles, which you tend to see more here in the United States in early mills. But there's one in operation. I think this one is in Spain. But if you put the walls of a tub around a Norse mill, I don't have a picture of it, I apologize, but I'm going to go back. But again, 20 years ago when I was in Romania, there's a town in the west of Romania called Rudoria, which has 24 little tiny, like 8 foot by 8 foot, 10 foot by 10 foot mills with one of these Norse wheels in the basement, and on top of that shaft is a millstone. And these little tiny mills are owned by clans, by extended family units, and each household would get 12 hours a month that it's their turn to use the mill. So they have them divvied up that way, and people just come in with their grain that they grow, and they grind it up during their 12-hour shift, and then they move on. Anyhow, you put the walls of a wooden tub around that wheel, and it gets more efficient because the water doesn't just splash away, but the walls of the tub keep it pressing against the paddles of the wheel, and you get more work out of the water. More of the wheel is suffused with water instead of just where it hits. It continues to push until the energy is expended, and the tub has no bottom, so the water just falls out the bottom. So it's a good, dependable wheel, easy to build, easy to maintain, moderate efficiency. Like the breast wheel, it's a good compromise. I have one in the basement of our carding mill at Old Sturbridge Village, and it's a very compact wheel. because it's can be put inside under the mill. It's out of the weather, so it tends to last a lot longer. You don't get the degradation of weather on it. You also have very little problem with ice and snow. It's a very dependable wheel. Not very powerful, but nice and steady. In the 1820s, the French start experimenting with a more efficient water wheel, looking at snail shells that are what our scientists call turbinates. Their shells, of course, spiral around, and that's why we call these spiraling water wheels, where the water is going in a whirlpool type fashion, turbines, from that shape of crustacean, shellfish, I don't know, mollusk. There we go, mollusk. Thank you, and I'm glad there's a biologist in the crowd. So anyhow. The nice thing about turbines is they are very efficient. They can get over 85, modern ones 90% efficient, which is a whole lot more efficient than gasoline engines, for example. They're a very, very efficient way of harnessing the potential energy in water by basically very carefully directing the water. So you don't get a lot of splash. You don't get a lot of turbulence. There's just energy going to waste like you see on all the traditional water wheels. The French were perfecting these, as I said, in the 1820s. In the 1840s, they start experimenting with them at Lowell, at the great textile mills there. And as the 19th century goes on, there's quite an industry here in New England, dozens and dozens of companies building different makes and designs of turbines to more efficiently generate power from falling water. And of course, we still use turbines today. When you think of a nuclear-powered aircraft carrier or a nuclear-powered submarine, people will say, oh, the turbines are an old-fashioned technology. Well, tell it to the United States Navy, because those nuclear-powered warships are all running on turbines. In fact, it's a steam turbine. It's not a water turbine, but what steam? But gaseous water that's under pressure. But the point is, it's still very similar. The idea of turbines is that they are very, very efficient. Anyhow, so you just have to control the water flow, and that's how a lot of electricity is still generated. In fact, these old turbines you often find rusting away in streams next to mills or where mills used to be. There's a lot of different styles. Oftentimes, the thing about a turbine is it's an enclosed system, so that it really controls the flow of water and reduces the amount of turbulence and water going to waste. And there's dozens. These are just half a dozen different styles, basic styles of turbines. There's more than you can count, and different patents have been taken out on them. But as I said, nowadays they often make them out of stainless steel, so they last longer. These things can be the size of this room or larger. And it's also very often how they can store the energy created by nuclear power generation, which are using turbines from the hot water that the nuclear reaction does to generate electricity. But the problem with nuclear power plants is they take a long time to start them up and shut them down. You don't just turn a nuclear power plant on and off. And we don't have good large-scale battery technology in our world yet. And so what a lot of nuclear energy would either go to waste on off-peak hours. And so what has been done in a lot of places, like Northfield Mountain in west of here, in Northfield, Massachusetts, is they basically took a big hill, scooped a lake out on top of it, and then the thing to remember about one of these turbines is if you put water under pressure into it, it turns. If you put energy into it, it pumps water. So a turbine can either be a power generator or a pump, depending on what's going on. Same thing with a electric motor. If you turn an electric motor, it's a generator. If you let electricity go into it, energy comes out. So what they do is they put these turbines and these electric generators at the base of these mountains. And when nuclear generated electricity is going to waste, what they'll do is put it into the motors, run the turbines as pumps, and pump water into this big artificial lake at the top of a mountain. And then, usually in the morning when we all wake up and turn on the television and brush our teeth and start cooking breakfast, we need more electricity. They open up the gates, water flows down from the top of the mountain through the turbine that now is generating power instead of being used as a pump, and the same motor that was, and the same thing that had been a generator, the thing that had been a motor pumping the water up with electricity coming out of it, into it, I should say, I'm getting all confused, allows it to generate more electricity with the stored power, stored as gravity in the form of water. So turbines are still very much with us. That was more than you needed to know. Sorry about that. Anyhow, we had our sawmill at Old Sturbridge Village. I showed you our grist mill and carding mill. I don't want to leave the sawmill out. We have what's called an outward flow reaction wheel. It's not really a turbine because there's not good hydrodynamic flow into it. It's basically just a big lawn sprinkler, one of those rotary lawn sprinklers, except it weighs 600 pounds cast iron. But water under pressure goes into it. The water exits through 6 jets, holes on the rim, and it spins around. The outward flow reaction was something that the English-speaking world was fooling around with in the 1820s and 30s when the French were developing the modern turbine. Once the modern turbine catches on in the English-speaking world in the 1840s and 50s, these outward flow reaction wheels tend to just go bye-bye. They're considered not as efficient and not as practical. Anyhow, to move quickly from the power generation to transmission of the power, as I mentioned, you can do it very simply with things like the Norse Wheel or tub wheels without using any gears, just have a direct drive. Same thing with sawmills, including ours. They'll often have a crank coming off the water wheel, and that just makes the saw go up and down. And you turn these things on and off by controlling the flow of water going into them. If you need to have your machinery run at a higher rate of speed or at a slower rate of speed than the water wheel can do, you go through gear exchanges. Big gears driving small gears speeds things up. Think of a bicycle. The big gears are in the front, the little gears in the back, and one rotation on the pedals makes the back wheel spin several times. So the bigger gear driving a smaller gear speeds things up. If you have a small gear drive a big gear, it slows things down. And in even the simple water-powered mills, they often go through a number of different gears for different parts of the machinery. Originally, these gears were made of wood, and then in the 18th century, the 1700s, they increasingly start using cast iron to make more compact gears. But the wooden gears remained in use well through the 19th into here and there the 20th century in the United States. And sometimes they'll use a combination of wood and iron. One thing that was popular for a while were what were called mortise gears. You'd make the body of the gear out of iron and then insert wooden teeth as a fail-safe. So if anything jammed up, the wood would just break and you slip out a new piece of wood instead of replacing a whole big, expensive, and impossible to repair gear. There's a better shot of a mortise gear. The other advantage of the mortise gear using some wooden teeth is it gets a lot quieter. Iron on iron is incredibly loud, but iron on wood is much more quiet and convenient. But anyway, there's another good example of a mortise gear. And belts. Belts and pulleys are even easier to build than gears because you don't have to worry about teeth. Much easier to build a belt and pulley system, which especially in the 19th century really caught on and into the 20th century for transmitting power. The advantage of the small electric motor is you eliminate this maze of belts and pulleys going down to machines like this little factory here, where every machine has to have its own set of belts and pulleys. And of course, those things are not only something that has to be adjusted and fixed and repaired and installed in the first place. With all these belts flying around, you can imagine if you're not paying attention to what you're doing, you or your clothes can really easily get sucked up into a belt, into that mess on the top, and you don't come out of it too well. So anyway, but for a while, like I said, for about a little over 100 years, the use of belts and pulleys was the norm in factories of all kinds. And again, because you can use different size pulleys to change speeds, you can have different speeds. That's how, a transmission in a car basically works. It's having different size circles turning other size circles, and by just slipping the belt from one to another, you can change speeds very easily, without no clutching, no grinding of gears, nice and smooth power. These machines could be turned on and off fairly easily by having two pulleys, one called the fast pulley, fixed fast to the shaft, and one the loose pulley that just spins freely. And then you just slip your belt by pushing it from one to the other to turn the machine on or turn the machine off. Basically putting it in drive or neutral. And if you want to change speed with a belt, it's real easy. All you do is turn it from a straight belt to a figure eight. You twist it, and then you get a reverse motion. So it's real easy to use belts and pulleys. That's why they're so popular. For larger distance transmission, not like miles, but yards, hundreds of yards even, for a while in the 19th century, they had these rope drives, both a photograph I show you and a drawing illustration. The ropes really sag a lot, so you have to have these supports in the middle. But it was a solution to a problem. So there are a lot of different types of mills. A lot of towns like Shrewsbury, as I mentioned earlier, throughout the past couple thousand years, people have used water power to grind grain. So grist mills, grist is just another word for grain, were really, really popular, really common. Somewhere in the 1200s, people figure out the idea of a crank, which allows you to turn rotary motion into reciprocal motion, or vice versa. If you think of your bicycle again, pushing up and down on the pedals through a crank is making everything turn. That's how these sawmills worked, is through a crank that just takes a saw and moves it up and down, instead of having two people pull the saw up and down between them. And then as the Industrial Revolution kicks on, at first with textiles and then with other things using power to do a lot more work. But again, grist mills are very, very common and the most ancient kind of water-powered mills. And a number of historic ones continue to survive as museums, as curiosities throughout the country. There's still thousands of these things in state parks and private parks and museums. The millstones, not to get into a whole lot of the grinding, but the millstones do have an intentionally cut face called a dress. There's a number of different dress styles that were used by millers to reduce grain. Basically what the dress does is turns the stones into rotary scissors. When one set of grooves spins above the other set of grooves, the grooves cross like scissor blades crossing, and anything falling through the eye, the hole in the middle, goes down along the grooves and gets scissored apart, and then blows around the outside and falls into a container, and you got your pancake mix. So there we go. So you go through the large water wheel, you need to speed up the rotation, so you go from that big gear to a small gear to speed up rotation, and then the grain from a hopper going through the stones, getting chopped up by those rotary scissors, if you will, and then the grain falling down into a meal chest. I'm not going to go through all the names of the parts of a mill. Like I said, every business, every profession, every trade has its own terminology. I will mention one, though, the mill rind. The rind is the iron bar that supports the weight of this top stone. It sits on the cockhead, this iron shaft here, and keeps the top stone from touching the bottom stone. Sometimes they're the thickness of a sheet of paper apart, but the weight of this upper stone is held on this iron crosspiece. And the iron crosspiece, the mill rind, of course, also balances the stone. And the United States Navy, in its Judge Advocate General's Department, the lawyers, their symbol is a mill rind. So if you ever meet a naval officer who's a lawyer, he's got a little mill rind on his collar to show that balance. You know, I mean, like you see Judge Judy, she's holding the scales. That's the civilian form of balance. The military likes something different, so they have the mill rind in the Navy to be that. But anyhow, there's a trivia thing for you, huh? So anyway, again, just another illustration of the simple Norse wheel and the millstones. Yeah, we don't have to get into all these gears. And there's other machinery that comes along, especially what are called bolters, basically power sifters that will, by passing the grain after it's ground through finer and finer cloth, sifts out fine flour from the bran. And here's Vanna showing you a bolter up in Ontario. So basically you've got a long tube covered with cloth, and the grain starts at one end of the tube, and as it slowly turns, gets sifted out. And you can have different blade valves at the bottom to have your superfine flour, your fine middlings, your shorts and middlings, and then the bran, the outer shell of the grain, gets out the other end and gets sold for animal feed or health food, depending on your, on your marketing thing. This is a wonderful mill up in Upper Canada Village in Morrisburg, Ontario. It's a combination water power and steam mill. Upper Canada Village, like Old Sturbridge Village, is not a town caught in time, but rather a compilation of old buildings to make a slice of life. And when they built Upper Canada Village in the 1950s, when they put in the St. Lawrence Seaway, they had water power for 2 mills, and then they got a 3rd mill and didn't have enough water power. So what they did is they moved in a mill that had been both a steam and water-powered mill. And so they'd run 2 mills in the morning, and then in the afternoon they'd run all the other mills, but use their steam engine to run this one. And the man who had the 3rd patent from the United States Patent Office was this fellow from Delaware named Oliver Evans, and he took credit for having the automated flour mill. Some people have called it the first automated factory. Basically, he had patented and invented machines that would move grain through the mill. And he used the same technology that, I did it again, that Marcus Vitruvius described 2,000 years ago, but he had machines to move grain from one floor to another and to sift it and to pack it and do all this other things. There's a story, it's probably apocryphal, but a lot of things that are apocryphal should be true, that a man had heard of Mr. Evans' amazing mill, and they went to go see it. And they went to where he lived and found a mill in operation, and went in on the first floor and started, hello, is the miller here? And nobody, so he goes upstairs and he sees all the machines working and the grain being ground and the grain being cooled and the grain being packed and all this other stuff. He goes up and down all the layers of the mill and he can't find anybody. But the mill's doing fine without anybody. He goes out and outside, he sees a guy plowing, and he yells at him, hello, can you help me? He said, well, sure. And he came near the fence, and he said, I'm looking for Oliver Evans. And Oliver Evans said, you found him. The mill was so automated it didn't need him. But he got rich selling patent rights, and he almost went broke hiring lawyers to defend his patent rights. But a lot of people, including George Washington, paid him for the right to use his advanced machinery to make advanced flour mills. And he also, along with a millwright, a guy who built mills for a living named Thomas Ellicott, in 1795, published a very successful book called The Young Millwright and Miller's Guide, which for historians and millers like me today is an invaluable resource because it's not only full of descriptions, but wonderful detailed drawings of how mills were built and how they should be built and how they were used. Another use that water power was widely put to was running machinery, was sawing lumber. At first those up and down saws, and then later on circular saws. Sometimes they would, if they had enough water power, they would do what's called ganging the saw, putting one sash, one frame with several blades in it to slice the lumber. Most mill sites didn't have enough power to gang a saw, so they just run a single saw. But it's very simple. Like I said, a water wheel, a crank, and you push the saw up and down, and it makes lumber, just like doing it by hand, except nobody's arms get tired, nobody gets bored, nobody gets distracted, so you get a lot more lumber cut in a day. Just a little illustration of how our mill works at Old Sturbridge Village with that outward flow reaction wheel, that sort of giant lawn sprinkler idea. But anyway, the circular saw concept goes back to the 1500s. The problem is that it's not until the mid-1800s, the middle of the 19th century, that metallurgical technology is advanced enough that they can make large discs of steel thin enough and flat enough to make a practical, large circular saw. It's one thing to have a little one that can cut boards in half, but to have one large enough to slice logs up is something else. Also, they got to understand that when you start taking this big 4 or 5 foot disc of steel and spinning it, everything is going to get deformed, especially if it gets a little hot. And so they've got to figure out how to adjust for tensions in the metal and the centrifugal force, which they do by actually hammering it and making it very slightly concave. And as it spins, it flattens out. That's a lot more complicated than just let's cut some teeth in a disc. But anyway, so having the circular saw cutting continuously instead of only half the time like an up and down saw, it's much more efficient. Another use of water power was brushing out wool, which is called carding, basically aligning the fibers so that you can spin it into yarn. These were another popular mill in rural New England towns from the late 1700s into the mid-1800s, when most people decided, why should I spin yarn? I can just go to a store and buy cloth, because all the other steps in textile production have been mechanized as well. But for a generation or so in the late 1700s, early 1800s, they were very, very popular, very profitable. These basically power brushes that untangled wool. And even more long-lived than that were fulling mills from usually about the 1500s in Europe on, that are basically water-powered mallets, big wooden mallets, that pound the dickens out of wet wool cloth to make it fuller, to make it shrink, to make it less a mass of interwoven threads and more into what we think of as cloth. You know, it basically gets it full. It shrinks it and mats the fibers together, felts the fibers together. Think of a pool table cover, you know, or the cloth on a pool table. That's heavily fulled wool. You don't even notice really that it's cloth. The idea of the fulling mill goes back to late medieval Europe. This person is contemplating the wonders of the fulling mill. But basically just big wooden mallets that the water wheel would tap its lifts and then lets fall. Lifts and lets fall and pounds the heck out of the cloth. And they also used water power to lift and let fall iron hammers that would make a blacksmith's work much easier. Because again, the water wheel never gets tired, never gets bored, never gets distracted. And if the smith only has to manipulate iron under this heavy hammer, much bigger than anything he could lift and let fall, he can get a lot more work done. Nowadays, blacksmiths have these other trip hammers that they can forge their iron with. But this was how things like shovels and axes and such were made in some parts of the world into the mid-20th century. So it's a very enduring technology, having a water wheel let a hammer lift up and then let it fall and do work. And of course, the Industrial Revolution happens in Great Britain in the second half of the 1700s, and then it spreads around the world, especially here to New England. And I don't have to tell you how many thousands of large factories have come and now gone across New England, initially using water power, oftentimes using steam as a backup, and then as they need more power and the river won't cooperate, using more steam engines to run all these masses of machines that were generating millions of yards of cloth and giving people employment, but also maiming people and killing them in this mass of belts and spinning machinery. But here's a happy little machine shop. I like this guy here. This is obviously before Social Security. I love that beard, you know. Don't get that too close to the lathe. Good gosh. Anyway, we don't have to beat this to death. But of course, most mills now have outlived an economic purpose, and have oftentimes gone to rack and ruin. And this is how we often find old mills that were once very profitable, very centers of neighborhood activity in towns, sometimes factories, sometimes these little smaller mills. Oftentimes they succumb to fire, either intentional or unintentional, and are no more. And sometimes they succumb to flood, because that's the problem. If you're using water power, water is powerful, and sometimes we can't control it. Much as we like to think we can control nature, oftentimes nature is controlling us. And mills are vulnerable to flooding, like this one up in Vermont not too long ago. But, of course, the water still remains a good source of recreation. Oftentimes, water backed up behind dams that once ran mills is now good for swimming, kayaking, canoeing. On larger water courses like the Connecticut and even larger rivers out west, it's still generating a lot of power, mostly now through electricity, but still generating a huge amount of energy for our society. Home hydroelectric is something you don't see much of in Massachusetts. Massachusetts has the strictest wetland protection laws in the country, and that and other regulations make it almost impossible to use home hydroelectric generation. In a lot of other parts of the country, people can get these little tiny turbines, either made themselves or buy them, and hook them up and get an electrician to come up to figure out how to, wire it into the grid, or at least into their house off the grid. But it's almost impossible to legally do in Massachusetts now, so I'm not going to get into it. A lot of museums, of course, are built around old mills, and a lot of museums make their living now, or at least a lot of their living, by renting themselves out for special events like weddings. We don't do weddings in our mills at Old Sturbridge Village, but we do rent out our meeting house for a lot of weddings. The fourth mill here in the upper right is our cider mill. It's powered by a horse, not by water power, which is why I haven't mentioned it till now. But anyhow, but a lot of other mills have survived as museums. The red one is Old Red Mill Village in New Jersey, and that's King's Landing in Ontario, and of course the National Park at Lowell took in the old Kirk Boot Mill. Boot was not a boot manufacturer; it was the name of the guy who owned the mill. Boot with 2 T's, and now the National Park Service rents out part of it as office space, and part of it is a museum. They have 80 circa 1920 dresser looms running and clacking away. When you buy your ticket, they literally give you earplugs because they're so blessed loud. If you haven't been, it's really cool. A lot of mills survive as restaurants today, of course. You can't swing a cat in some areas without finding an old mill restaurant of one form or another. And it's scenic because the ducks are on the mill pond and on the stream, and it's cute. Luckily, a lot of them survive today, being second use, turned into condominiums, turned into retail space. The lower right is actually in Sturbridge, Massachusetts. That's a mill built by 2 brothers by the name of Fisk in a little part of Sturbridge called Fiskdale, logically enough. It was built in 1827. In the 1930s, one of those hurricanes took off its 5th floor, and it wasn't worth it in the 1930s to rebuild an over 100-year-old mill, so they just put a roof on the 4th floor and called it a day. But you can still see where the 5th floor was. Anyhow. And a lot of mills have survived by being turned into homes. It's another way they often get used. And sometimes they're under archaeological investigation. That's been a lot done. And of course, Mr. Kirk, as we all know, did an extensive survey of Shrewsbury here. And if I read you online correct, there was 9 sites you identified. Yeah. So yeah, you can go online and see all his wonderful maps and analysis and photographs and the like. Most old mills, if they're around anymore, are sort of gobbled up. It's amazing when you just walk some places you think are nowhere today, and once it was a busy hive of industry. Like I said, at one time there were thousands and thousands of these mills. Most every town had at least a handful, if not dozens of them. And that's pretty much it. You've been very patient. I've talked over an hour. I apologize for that.